My name is Robert Stockwell, and this is my Chem 268 Organic Chemistry Lab MSIR introductory video. First, we will look at an unknown molecule, and we will use our MSIR data to try and determine what the composition and structure of that molecule will be. We begin by looking at the mass spectroscopy data presented before you. The mass spectroscopy shows the relative presence when this molecule is broken down into ions and their relative prevalence, and as a result, stability in a compound. So, the most important thing we are concerned with in this is the very first one, which is our M+, or our very first peak, being 123. And this will represent the full molecular mass of your compound. The second part we're concerned with is our base peak, or our most stable ion of our molecule. These two together will give us a decent idea of maybe some functional groups, and it'll allow us to at least get some preemptive structures or theories that we might prove to be the actual structure. So we can look at the space in between these two, and that'll tell us some of the substituents that may have blown off. By looking at the spaces between the groups, we can kind of understand what may have been breaking off as it ionized. So, you can kind of either do the math and add up all the molecular weights of all the possible substituents, or you can simply find a cheat sheet. And on this cheat sheet, it would appear that this 15, or that this might be the 15 that had broken off in our original things. So that was the first most unstable group that found it easiest to leave. Potentially, because as you see before you, there isn't any 28 on this cheat sheet, which means that 28 could be a very simple difference. It could be this 29 minus a hydrogen. It could be all sorts of things. The point is that we are not totally sure. So, any interpretations you make with this that aren't backed up by either your IR or other data, take with a grain of salt. But what it really does allow us to do first is to determine the potential chemical structure. And to do this, there are some tricks that you can tell that help you understand it. You can by the fact that the M+ is odd, that kind of clues us in that there's likely a nitrogen in this substance. This will be confirmed by our IR spectra, but right now we're just going to assume it's there due to the odd number present. So, we can take our total mass of 123 minus the nitrogen. Then we can divide that 109 by 12, and any remainder that we have left will be potential hydrogens, as follows. We have either 9 carbon with a remainder of 1 hydrogen, or 8 carbons with a remainder of 13 hydrogens, plus the nitrogen gives us the structures you see below. Now the other possibility that presents itself is the addition of oxygen, which we can't readily see from looking at our mass spec sheet. But what we can do is just add it in and see if it works. So we do that the same way we did the nitrogen, by subtracting the oxygen first and then the nitrogen, or in whichever order you want, and then taking that final remainder and dividing it by 12 to get 7 carbon with 9 remaining hydrogen, as well as the oxygen and nitrogen. The next step we can perform is calculating degrees of unsaturation. You do this with the formula 2 times the number of carbon plus 2 plus the number of nitrogen minus the hydrogens minus halogens divided by 2. So we can start with our first one, C9HN and calculate the degrees of unsaturation. So that would be 18 plus 2 plus 1 minus 1 divided by 2 is 10 degrees of unsaturation, is very high, and also might not even be possible. Next, C8H13N calculates down to 3 degrees of uncertainty, which is very reasonable and very possible. Last, we're looking at our C7H9NO, which calculates out to 4 degrees of uncertainty. Now, the C9HN probably isn't possible because I don't know if there's any real way to do that with only one hydrogen. But that still does leave us with the two remaining ones of C8H13N and C7H9NO. And both of their degrees of unsaturation are reasonable, so to actually determine anything further, we have to move on to our IR spectrum. And our IR data that we have is formed when energy in the form of light is shined onto or put onto a molecule and it vibrates at different frequencies. And the different frequencies of vibrations can help us indicate certain substituents and functional groups that are present on the molecule. We interpret IR data by breaking it up into 5 spectrums. These 5 spectrums, or these 5 sections, allow us to just kind of partition out the data so that we can look at it a little bit more piecemeal. So our very first part, and then the very last piece is the fingerprint data, which is generally mixed up to the point where you can't do much of it unless you're a machine or you have very specific knowledge. But we'll ignore it for now. So the first group has these very long spikes. With any kind of data on interpreting IR, there's a million different trends that kind of clue you in onto it. But this one indicates the presence of some kind of amine group. So we're likely going to have some kind of amino, either with hydrogen or, I believe, the possibility of a secondary hydrogen present. And that's what that tells us. Now the next section we have is the second group. And this gives us a little bit more information. By this tiny little section right here indicates the presence of sp2 groups, or anything with a double bond. And the second group indicates the presence of sp3, or single bonded things. So this is very, very common to see both of these together in anything that is a alkene. And we have multiple double bonds and single bonds. Now, we don't know which one it is though, because we need further data. So we can move on to section 3. Now sections 3 and 4 actually don't have much, but that's also an indication. Group 4 does not have the presence of a double bonded oxygen, otherwise you would see a rather large spike coming down right here. And since that is not there, we know that it may not be oxygen or it may not be double bonded. And with the lack of a alcohol in around group 1 and 2, which would be a big looping tongue over here, we know that if there is an oxygen present, it is going to be an ether, or it will be the other one. Now, we move on to our fourth group, or our fifth group. Our fifth group has two important things. First is this spike right here indicates the presence of a nitrogen-hydrogen bond. So the fact that it's kind of short, it only goes about halfway, indicates that we likely only have about one nitrogen. So that means that our approximation during our MS spectrum, where we guessed that there was one nitrogen because of the odd number, means that we were likely correct in doing so. And the other important thing here, actually really the big money maker right here, is this big spike right here, which right on the 1500 indicates the presence of a benzene ring. And that's really going to help us a lot. That'll explain our sp2 and our sp3 orbitals and a lot of our degrees of unsaturation. So, looking back over it, we likely have the first amine group. We have some double and triple, or some double and single bonds. We have some double and single bonds that at least form a benzene ring, and we have a nitrogen, which is probably explained by the amine group. So now, putting it all together, if you have other things, or the kind of where I'm pulling some of my information from, there are some quick reference sheets such as our IR spectroscopy provided by Common Chem, and it shows some of the common regions and spaces that you will end up finding a lot of these things. This is where you would end up finding if there was an alcohol present, if there was a carboxylic acid, if we did have that carbon-oxygen double bond, we'd have that spike, or we have our aromatic spike that we were looking at right here. And then it does give us some information about the fingerprint region if you like to venture into that. However, now that we've looked at ours properly, we can move on and see back to our chemical compounds. So before, just due to feasibility, we had already kind of eliminated this one. However, we can continue to look on and see that we have the other substituents that we decided that we likely have. This 15 is being back from our IR, where we saw that a 15-pound thing, or a 15-pound, that would be a really big substituent. A 15 atomic mass thing broke off. So we have our C8H13N has 3 degrees of unsaturation versus our 4. And now we can automatically disqualify this one as well because of the presence of the benzene ring. The benzene ring having 1, 2, 3 degrees of unsaturation seems perfect, but the ring itself also counts as 1. So that means that the benzene ring alone provides 4 degrees of unsaturation, which is perfect for this one. So we can put it all together. We have these groups, we have an oxygen, and we have a benzene ring. So starting out with our benzene ring, we know that this gives us 2 potential structures. One with our nitrogen on this side, and then at any point it could be bonded. We could have our oxygen bonded to any of these. However, that's not the main thing that I'm talking about, because that oxygen could just as easily be bonded to any one of these. So, the other group that it could possibly be, or that we're possibly looking at, is back to that benzene with either the nitrogen on this side and then oxygen methyl substituent, or the opposite being true with it being the carbon and then the oxygen and then the nitrogen substituent. And how do we determine which one is attached to the oxygen? Now, we know that if this functional group is attached to the oxygen, it's going to be less stable because that oxygen is a little bit more electronegative. And that single bond is going to be a little bit further apart, causing it to be a little bit more likely to let go of that substituent. And if we remember correctly, the substituent that was easily let go was initially this one, a 15 atomic mass substituent was released. So we can kind of guess that the one let go was going to be the methyl group that we see present. And this methyl group, being the first thing to be released, is likely going to be part of, or is likely going to be attached to this oxygen, giving our final structure to be one of the conformational isotopes of this.